Let's continue our study of methods and references by refining search. Here's the problem statement. E-commerce sites often permit you to start an initial search and then refine it. That is, to be more and more specific about exactly what it is that you would like. So, for example, if we go to Land's End, we'll see that the checkboxes on the left are actually search refinements. So here we are at the Land's End site. Notice that I've picked women's shirts and blouses. If, for example, I choose only things that come in regular sizes, we're refining the search. That is, we're finding a more and more specific search. I could then, for example, only want things with 3/4 length sleeves. You'll notice that the relationship between size range and sleeve length is actually an and relationship. It's looking for things that fall into both of those categories. Whereas, if I check that I want 3/4 length sleeves or long sleeves, we have an or relationship going on. So you have both ands and ors working on this site. If, for example, I uncheck that box, it's taking me back to a previous search. So search refinement is actually a very important and interesting problem. So let's write a program that allows a user to search string data stored in a file and repeatedly refine the search, one word at a time. Of course, our first question is what our test data is going to be. Once again, I went to Project Gutenberg, and I wanted a nice long book that should provide sufficient data. I picked Little Women this time by Louisa May Alcott, but you could pick something different. So we certainly want to search for words that are in the book. We could use things like the main characters' names, for example. And we can search for words that aren't in the book. So any modern word will work well there because this is a relatively old book. My personal plan is to search for computer because they didn't have computers back then. Now the next thing we want to consider is whether case matters or not. We could implement the program either way. If we decide that we do not want the program to be case sensitive, what we should do is store all the data in either lowercase and uppercase, and then do all of our searches in either lowercase or uppercase. In this case, though, I'm going to leave it as being case sensitive, so our searches will in fact be sensitive to case. Now, these are things you have to think through in every different application. This may not be the right decision, for example, for a website search, where you want to bring up as many things as possible to help the user find them. The methods we're going to need to do this are ones that are familiar from previous programs we've written. For example, we certainly can read the data from a file, and we want to be able to display the results. In the sample code that I wrote for you, I used a for each loop for that, just so you could get a little bit more experience seeing those in action. It's a very nice kind of a loop for something like that. And we need a method for the user interface. Now, I called this perform search refinement, so it needs the data and it also needs the scanner object so it can interact with the user. The only really interesting method here is the search method. So it's going to take the array list called source and look for the target string. So let's go and write that method. Here we are in Eclipse, and notice we've got our search method up here. So we're going to want to step through this array one index at a time. Now I am going to do this based on indices, although there are other ways this code could be written. If we find something that doesn't contain the target, we want to remove it from the source. That way we don't have it to work from. We'll have an int index, which is initialized to 0, and we'll let the loop repeat as long as index is less than source.size. And if source, you know what? I'm not going to write it that way. I'm going to write it a little simpler way. I'm going to create a string that I call line and do source.get of index. Now, the reason I'm doing it this way is because I found that students have a lot more success doing one thing on one line. So when you start nesting complicated expressions within each other, it gets really easy to lose track of which object is of which type. So by declaring a reference line and storing the reference in there, we are actually able to see that this is a string object really obviously. And I found that people who write code this way tend to have better success. So let's stick with this. So if line dot contains target, well, now let's think about it. Do we want to do something when line contains target or when it doesn't? I think what we want to do is remove when line doesn't contain target. So let's put a not in front of that. And what we're going to do here is source.remove at the given index. Now, we need to think carefully about what we should do next. I think most people, if they wrote this code alone, and by the way, certainly the first time I wrote it, would just have done this, set index equals index plus 1. But you need to be a little careful. Because we are removing something at the index from source, that means the things at the larger indices are going to be shifted over and are going to fill in that spot. So in the case when we remove something, we do not want to increment the index. We're going to need to check that same index again because now there's a different value in it. So what I'm trying to say here is that this belongs in an else statement. And of course, whoops, that would be a silly thing to do, wouldn't it? So now we're incrementing once, but only when the data item isn't removed. So that looks pretty good. Now, at this point, we probably should test the program, but I have bigger fish to fry, so I'm going to go on and do something else. Just remember, testing more often is going to make it easier to debug your programs. So if you were doing this on your own, this is definitely a time you would not want to skip testing. Now, there's a serious shortcoming with this program, and that's the user can't go back to a previous result. And that is an extremely useful thing to be able to do. So the problem here is that we have only one ArrayList of string object. So let's take a look at what the parameter passing looks like right now using a memory diagram. So we're looking at the parameter passing between the main method and the search method. So here is the memory diagram. Notice in the main method we have one reference data that points to the array list that's in the heap. Remember that the heap is where all the extra memory is, and so that's where all of our items get constructed from. So we've got our array list. Now I've just put some sample data in here, 1, 2, 3, 4. That wouldn't be the real data because of course those wouldn't come out of the same search. So we have the references to the strings. Now in the search method, we have a reference called source, and it points to that same array list. So the main method and the search method are both using the same array list. So when we make changes in the search method, that means that the main method's version of this array list also gets changed. In other words, once we've removed things in the search list, they're gone in the main method too. Now the reason that is true is because of these arrows. The arrow right here and the arrow right here that show us that both of these methods are using the same object, even though they have different references. So what we're doing in this program is we're passing the ArrayList of string by reference. When an object's reference is passed to a method, both of the methods share the object. We saw that in the diagram. Now this sharing ends if a constructor gets called, and we're going to see that later too. Now this is very efficient for memory usage because references are teeny tiny. ArrayLists, on the other hand, can be really big. The problem in this case is it makes it impossible to back up because once we've removed elements from that array list, they're gone forever. So the next thing we need to do to create a backup feature is we need to store the previous array list objects. So we're going to use an array for this. Now this is kind of an unusual design decision, and I'll explain why a little bit later, but we're in a chapter on arrays, so certainly array has to be involved somewhere. So if we have an array list of string called previous searches, here's how we construct it. This construction is a little bit weird. This is a very strange Java quirk, and that is that you give the generic on the left-hand side when you're declaring previous searches, but you don't give it on the right-hand side when you're calling the constructor. Now this is something that is completely unanticipated. This is something that you never would have guessed. And by the way, if you were doing a test, I wouldn't take off any points for making a mistake, like putting the generic in here, because that really would make sense. This is something that you'll learn in your next class on Java, and eventually this will make sense. But for right now, just trust me that that's the way it's supposed to be done. So notice here I've declared the reference previous searches, and I've also constructed an array to a fixed size. You can tell it's a constant because it's in all caps. Now when we do a new search, we need to save the previous ArrayList string to the array. Now that's going to change the signature of the ArrayList method because now we need to return that ArrayList too. Now, as we go to implement this, we need to make sure we understand exactly when we're going to put things into and take things out of the array. There are actually two different ways it could be done. One choice would be to put in all the searches immediately when you do them. The other choice is to put the previous search into the array just when you do the next search. Now, either one of these can be done correctly, but where you're going to get in trouble is when you do a hybrid, when you sometimes do it one way and other times do it the other way. So it's important to have a plan going in. Now, the plan I'm going to use is putting the previous search in when the next search is done. Like I say, neither one of these choices is better. It's just important that we're consistent. We're going to go to our search method and change the return type. So now we want to return an array list of strings. Now, to make the compiler happy, we'll return source. The other thing we need to do is we need to update our Java doc. One of the problems you run into when you start making changes to code like this, which is basically code maintenance, is that it's very easy to forget to change the documentation. And when you do that, then your documentation doesn't match your code. There's a saying in computer science that when your documentation doesn't match your code, they're usually both wrong. Now, what we mean by that is that when those two things get out of sync, it means that when you were writing the code, you weren't paying careful attention. And if you're not paying careful attention when you're writing code to details, like the documentation, it's likely that you made mistakes writing it. Now, of course, we're being a little sarcastic with this, but it is actually something to consider. So we're going to return the source array with only strings that contain target. So there we go. Now our documentation matches our search, and we're happy. Now the other thing we need to think about is how we're going to change our user interface. So first we need to find our user interface. And it's right down here at the bottom. It's called Perform Search Refinement. So you'll notice that I created a constant. Now I just put it in this method because this is going to be our whole user interface, and so this is a good place to have that. We don't need to have it in the main program. If you put it in the main program, remember you'll have to pass it in as a parameter. Then I did the construction here, just like I showed you on the previous slide. Notice that we are missing the generic here, and Eclipse is giving us a little warning about that. The other thing to notice is we need to keep track of the size of elements in the array by ourselves. It's not like an array list where all that gets stored. This time we have to keep track. So I created a string called answer. It's going to get input from the user. I initialized it to yes to get us into the loop the first time. I've got some little comments here that you may read. Basically, when the logic gets complicated, more documentation is a good idea. If we get into the loop, what we want to do is ask the user if they want to refine the search or go back. And then we read that from the user. If the answer isn't back, then we're going to need to do something to refine the search. Otherwise, if the answer is back, then we need to go back. Now, I had commented out this search previously because I changed the signature on it, and I didn't want it to put up error messages when we were writing the search method. So there's our search. So let's think about what we want to do. Well, the first thing we need to think about is putting things into the array. So the array is called previous searches, and we're going to be setting the value at size to data. So this way, we're storing the reference data in our previous searches array. And of course, size is going to equal size plus 1. Now, whenever you write code with an array, you have to be very careful to not step off the end. Arrays are different than array lists. Arrays do not reconstruct the array to a larger size like array lists do. So really, we need to put a guard in here. And that is, if the size is less than size. Now let's think about that. If we have size minus 1, we can put the data in there. And so that actually works. Now we also have to think about what we're going to do if this doesn't work. Now we could have a lot of complicated strategies, but I think the easiest one in this case, and let's make a comment here, that there's enough space in the array. No more space in the array. Really the only thing we can do at this point is let the user know what's going on. We probably don't want to refuse to let them do their search, so we're going to mess with the backup, but at least they'll still be able to do their search. So they do their search and then they return the result. Now let's think about what happens if they're going back. Well, what we're going to do is data equals previous searches of size minus 1. And then size equals size minus 1. There's one other thing that we really should do here, and that's previous searches of size minus 1 equals null. I'm going to move this line up one line. Since we had changed size, we need to be careful to use the old size. What that does is it takes the array reference that was stored in previous searches and it removes it. Now that turns out to be important because Java garbage collects things only when there are no references to it. So if you don't do that, what happens is some array lists will get left in memory that shouldn't be. These are subtle things and things that are hard to learn, but it is part of becoming a professional in doing this. So in this case, we go back to our previous search, we set that value to null, decrease the size so that we keep the size correct, and then we're going to let it go around again. So basically we don't do a search in this. The returning back one is the function of this part of the code. Then we ask the user if they want to continue. So this is all looking good except for one thing, and that is, how do we know that this size minus 1 is legal? Like I say, every time you put an index in an array, you have to think to yourself, how do I know that size is at least 1? Well, in this case, you really don't. And so what we need to do is to put a guard in it. So if size is greater than or equal to 1, you also could say if size is greater than 0, if you like that better. Then these get indented. If size is not bigger than that, then we need to let the user know. So we'll give them some feedback again. There is no previous data to go back to. You always want to keep the user in the loop and let them see what's happening. There we have a nice little group of code using an array. By the way, this is very typically something that is done with an array. The reason is because arrays are fixed in size. It really does make sense here to keep this fixed. It's very unlikely that somebody's going to go more than 10 levels deep in a search. And so this really makes good sense. So let's run our program. Now I'm going to do our test on the file called Little Women Excerpt. If I can spell it correctly anyways. What I did with this was I just took the chapter headings out, and so that gives me a nice reasonable search to follow. So let's search for 20. That looks good. All those lines actually have 20. Then let's continue and search for 2. That should give us just one line, the one with 22 on it. And let's continue. And let's search for computer. So this is something that isn't going to be in it. Now, you'll see one shortcoming with our user interaction, and that's that we didn't give the user any feedback when there was nothing in the search. So that's a problem. We're going to want to fix that one. But let's keep testing. So let's continue and then go back. Now notice after we went back, we also didn't display the result, and that's something else we want to fix. So let's go back and do a search for 2 again. So somehow our back isn't working correctly. So we're going to need to debug that. So let's stop the program and let's fix some things. So first off, after we go back, we want to show the result for data, because it's not fair to the user to not see where they're working from. And notice that was causing us, or may have been causing us, some problems in debugging. The other thing we wanted to do is to change our display method so that when there is no data displayed, we actually say something to the user. So this is the show result method. So let's fix that one too. If data.size equals 0, system out print line, there are no results to display. In fact, we could even return at that point if we wanted to. So there's some nice code for that. So we fixed a couple of things. Let's go and do some debugging. Or sorry, let's go and do some testing. So we're going to do 20, and that's working correctly. We do want to continue. Let's do our search for 2. That's working correctly. We want to continue. Now we're going to do our search that won't give us any results. Notice it says there are no results to display. So that really is very helpful. We do want to continue. So let's go back. Now it still has no results to display. Let's try it one more time. So something's going wrong there. Somehow our backup feature isn't working quite right. So let's go to the search refinement method and see if we can find what the problem is. So when the answer isn't back, we go and do another search. Now it looks to me like that's going correctly. Let's make sure we got our size initialized correctly at the start, which we did. So that looks good. So data is previous searches of size -1. Ah, I see the problem. Look what I forgot. When we do previous searches, remember size is unit indexed and the indices are 0 indexed. So basically we were storing the data in the wrong place, and that's why we're having difficulty finding it. We've stored it one position out further than we should have. So we should have stored it at previous searches of size -1 and then incremented size. Then notice here we'd be retrieving it from size -1. So as always, it's the boundary conditions that kill you in programming. Let's run the program again and see if things are working better. So this will be little women excerpt dot text. So we'll search for 20 again. Uh-oh. And now we've got a problem. So notice when size is 0, we've got an issue. So that's the first thing that broke. So we need to think a little bit more about our logic here. When size is 0, we want to put it at size of 0. So maybe that wasn't where our problem was. Let's think through the whole problem. So we put it at size of 0 and then size goes up to 1. So when we're retrieving it, do we retrieve it from size -1? Well, we would retrieve from size of 0, which would be size -1. So that's kind of strange. I wonder what's going wrong. So here, when we put it in, we go to size of 0. Then we create a new search. Here, with size is 1, we'd be pulling out of size of 0. Well, isn't that interesting? So what I'm doing right now is just carefully reading the code and thinking through every line to make sure we're doing the right thing. So if we're refining our search and our size is less than size, so this would mean size minus 1 would be the biggest thing that could go through here. That would be correct. Then we would say previous searches of size is data. That looks correct. Size equals size plus 1. Anytime we add something in, we're going to have to add 1 to size, so that looks correct. Then we do our search. Now remember, I'm making the decision to only store something if we're going to actually do another search. But I think I've been pretty consistent with that. So now if size is greater than or equal to 1, we get the data from size minus 1. That really looks correct. And then we set previous searches of size minus 1 to null. Now you might think that's a problem, but remember, because we've already put the reference into data, that looks okay. So maybe it's time to do a little debugging and see what's going on. So here we are in our debugger. We suspect that this is where the problem is. Where do we want to put our stop? I think maybe right about line 142. So notice I've set a breakpoint there, and now I'm going to run our program again. Remember that I'm going to pick the debugger to run the program. So this is little, whoops, better get the capitalization right. So we're going to do 20. We want to continue. And then we were going to go to 2. And we wanted to continue. And then we were going to search for something that isn't there. And we want to continue. And then we go back. And right here we are. So here is data. And notice there's nothing in it. You can actually see the contents of data here. Now, previous searches, on the other hand, has 3 array lists in it. Let's take a look at this one. This one is element data. And if you look very carefully, you're going to notice same object, same ID, same object, same ID. We have put the same reference into the array 3 times, and that's why we're having trouble getting back to our data. So we actually now have found the problem, and it's a serious problem. Let's go and look at it in terms of memory diagrams to help you understand what the difficulty is here. This is what happened in our program. Previous searches is an array. You see it right here. So this array is allocated on the heap, and what it has is array list references in it. The size is currently 3 because we've used the search 3 times, and we have our data array. Now remember, in our search method, we did not construct a new array list. We just returned the one that we already had. What this means is that the source in our search method, all 3 of the references in our heap, and data are all pointing to that same single array list. As a result of that, once we had removed all these elements from the array list down here, what happens is we've removed everything. We still can't back up. So the problem here is that we're sharing an array list when we should not be. What we need to do in order to be able to back up is to construct new array lists. Now, problems like this are incredibly difficult to find. And in fact, if you did not have memory diagrams at your disposal, you might have a very difficult time understanding what had happened in this program. But in essence, what happened is even though we were returning a reference because we didn't create a new object, all of our array lists are the same object. And when we remove everything, it's gone from everything. We created space to save the references to the objects, but we've only called an array list constructor once. That means there's only one array list object. And what we've done is we've saved its reference many times. This is a very typical mistake to make. If we want to be able to go back to a previous search, we're going to have to save a separate ArrayList object. It's going to need to be constructed inside the search method, and that new reference is going to be returned. And then this reference can be saved in the array. So let's go fix our search method. So here's search, and we're going to need to construct a new array list of string. I'm going to call it results. Now, I've got a hint for you when you're programming. Notice how we returned the parameter and didn't call a constructor? That is almost always a mistake in Java. So when you're returning an object like this, that means you usually are constructing it inside your method. Not always. In fact, there are examples in the Java API, particularly in the string builder class, if you want to take a look at those. But in general, when you return an object, you want to construct it inside the class. Now we're going to have to think through our logic a little bit, because remember, we were removing things before, and now we're going to be inserting them. So we're going to say if line contains the target, then result dot add the index. Whoops, and I guess I called it results. And here's the important part. We need to return the new thing that's added. Oh, and it's not index we want to add, of course. We want to add the line. That is, we want to add the string. Now, the other thing we want to make sure we do is update the documentation again. So here is better documentation. A newly constructed object with only strings that contain the target. Okay, so let's see if our search refinement is working better now. So we're going to go Little Women excerpt.text, enter the search refinement. So we're going to do our search for 20 again. Uh-oh, looks like an infinite loop. And I see it already. Think about what we did here. Because we're adding now, we need to treat our index differently. Now that's what happens when you don't read code carefully enough when you're writing it. So because we're now adding it to a new array, that means we need to go through the indices one at a time. And in fact, we could even use a fancier loop for this. So let's actually do that. Let's use a loop that's a little less error prone. For string s colon source. At this point, we don't need to use the index at all. If s contains target, then we do results.add of s. And at that point, we don't need the index. I see that I erased one too many curly braces. And we can just return results. Incidentally, in this particular case, all those curly braces are unnecessary. I'm going to leave them there because, as I've mentioned before, I think it's better practice to have more curly braces. But in this case, you'll notice we've made this only 3 lines of code long. So this for each loop really works out nicely when you're using it with array lists. Okay, so let's try our code again. So we're going to enter our search refinement. We want to continue, then we're going to search for 2. We want to continue, then we're going to search for computer, which gives us no results. We want to continue. Now if we go back, we're expecting to see 22, which looks good. So let's continue and go back again. And notice there's our previous search. And go back again. And there are all of our chapter headings. So it looks to me like our backing up is working just fine now. So we've tested our refining search. Of course, as always, we could do more testing than what we've done. Let's take a look at what the memory diagram looks like now. Now, I know this looks like a lot of detail and it can be a little bit overwhelming, but take a look at what we've done. Previous searches points to the array right up here. And now that array has two different array lists. Now these array lists are sharing strings. That's something we might want to think about, whether that's a good thing or a bad thing. So for example, this refined search, the one that's on the right, has two of the strings that were in the original search. And that search is now the one that's pointed to by data. So what we're doing now is we have separate array list objects. That's what that constructor call really meant. Here are some questions you might be thinking about. Why is it okay to have multiple references to the string objects but not to the array list? Well, the thing is with the array list, by having one reference to it, when we made changes, all those changes would be reflected. That's because array lists are mutable. That is, they can be changed. On the other hand, string objects are immutable. So we know that none of those string objects are going to be changed, and that's why sharing is okay. And in fact, this is why the Java Collections Framework was designed to use immutable objects. Now, another question you might ask is, are we using too much memory? And the answer there is really no. I'm going to go back to the previous slide. Notice, for example, that the only memory we're really using is just for these additional array list objects. We're not repeating the strings. Remember that while I'm showing little tiny things in the strings here, the strings could be quite long. And so those are not being repeated. There's only one copy of each one of those. These are the things that you can do because string is immutable. These array list objects, they're relatively small. And so that's really not so much of a problem. And of course, the heap is just references. So remember, references are tiny, so there's really no problem here with memory usage. What you've probably noticed here is that memory diagrams are our lifeline. We've really reached the point where we have to deeply understand objects and references to debug these programs successfully. This is a skill that takes substantial time to develop. So these memory diagrams are a very important technique, but I did demonstrate some other techniques too. The first thing you'll notice that I did was read the code thoughtfully. That has been proven to be the best way to debug programs, believe it or not. Sometimes people get so involved in the debugger and things like that they forget that carefully, strategically reading code is what's important. Tracing code, seeing what's in each variable at each time, I didn't demonstrate it this time, but we've done it in other programs, is another good technique. And of course, learning to use the debugger. So in this case, the debugger gave us the answer very quickly because we saw that all of our objects had exactly the same reference. That is, that when we removed all the strings from one object, we'd remove them from all of the objects because we were only sharing one object. So these are skills you need to continue to develop. Now, the last thing I want to talk about is using an array in this. There actually is a problem with this program, and that's that you do not usually create arrays of object types that have generics. In fact, Java doesn't like that, and if you read much on the internet, you'll see a lot of people disapproving of what we've done here. So it's very important to note that many Java programmers are only going to create arrays of primitive data types. I would like to point out, though, that the API does create arrays of objects. Particularly, a method like split in the string class creates an array of objects. We've used that before. It creates an array of strings. Now, in all fairness, string is very much like a primitive data type because it's immutable. But I do want you to realize that arrays of objects are created even in the API, so it's not completely out of bounds. I will say, though, that creating arrays of objects that use a generic is very unusual. A commercial Java programmer probably would have used an array list instead of an array in this program, and that's a modification that you might consider doing too. So keep programming.